Hello everyone and welcome to my video tutorial on Introduction to Graph Theory using Python and NetworkX. This is the fourth video of a series, Eulerian and Hamiltonian graphs. My name is Innocent. The motivation for the class today is that a good knowledge of the concepts listed in the objectives that will be stated next is essential for understanding some details of network and graph theory. It is also important to know some practical applications of the concepts covered. It is also important to know how to generate and plot and analyze graphs from file data. Learning objectives. At the end of the class, participants should be able to describe and analyze Eulerian graphs, obtain an Eulerian circuit using Fleury's algorithm, describe and analyze Hamiltonian graphs, describe and analyze tournaments and apply the concept to game tournaments, read and edge list network file data and use it to generate and plot undirected graphs, digraphs, and weighted undirected graphs. Contents: Introduction to Eulerian graphs, Eulerian graphs equivalent statements, obtaining an Eulerian circuit using Fleury's algorithm, Hamiltonian graphs, Ores and Dirac's theorems, tournaments, Radis and Camion's theorems, reading and writing network files, edge list undirected graph, edge list digraph, edge list weighted undirected graphs. Now we look at introduction to Eulerian circuits. First, we will define an Eulerian trail. An Eulerian trail is a trail between two distinct vertices in a connected graph if it contains all the edges of a graph G. The graph needs not be simple. Recall that a trail has a restriction that each edge be traversed at most once. A semi-Eulerian is a graph that contains an Eulerian trail. An Eulerian circuit is a circuit that contains all the edges of G. Recall that a circuit is a closed trail from our previous class. So we say an Eulerian graph is one that contains an Eulerian circuit. First example. In the graph we have on the top right here, graph A, E1, E2, E3, all the way down to E11 is an Eulerian trail. But the graph itself is not an Eulerian graph. Why? Because we say an Eulerian graph is one that contains an Eulerian circuit. And an Eulerian circuit is a circuit that contains all the edges of G. And we know that a circuit is a closed trail. So, why is it that the graph we have on the right here is an Eulerian trail, but it's not an Eulerian graph? Because the set of edges that we have here do not form a closed trail. Let's traverse the edges. So we'll go from 1 to 2, from 2 to 3 via E2, and then from 3 to 2 via E3, and from 2 to 3 again via E4, 3 to 4 via E5, 4 to 5 via E6, 5 to 6 via E7, from 6 back to 5 via E8, and back to 6 via E9. We get back to 1 via E10, and then we come to 4. So we started at V1 and we ended at V4. We did not end at V1. Therefore, it is not a closed trail, and that's what makes it not an Eulerian graph, even though it is an Eulerian trail. Another example, the graph we have here, graph B, is an Eulerian circuit, and B is an Eulerian graph. That is, we can traverse these edges to show that it is an Eulerian graph. So if we start from 1 and we follow E1 to 2, and then we follow E2 to 4, and we follow E3 back to 2, follow E4 to 3, follow E5 to 4 again, follow E6 to 5, follow E7 back to 3, following 8 back to 1, following 9 back to 5, and then following 10 back to 1. So we started at vertex 1 and we return back to vertex 1, and that's what makes it a closed tree. So that's the reason why graph B is an Eulerian graph. Let's look at an example in Python on how to plot these graphs. So we are going to call this multigraph 0.py to demonstrate multigraphs in NetworkX. So as usual, we do our normal imports. We import NetworkX as NX and matplotlib as PLT. Now we are going to create a set of nodes. We want to create the first graph we saw there exactly if possible. So we have nodes 1, 2, 3, 4, 5, 6. The first graph, which is A, contains 6 nodes. So we are going to say G is equal to multigraph. The reason why we are using multigraphs here is that if you look at the graph that we are trying to plot, from 2 to 3 has duplicated edges. That is, there are 3 edges connecting node 2 to 3, and there are 3 edges connecting 2 other nodes within the graph. Now, NetworkX also has something called multigraph, not really multi-digraph, but I tried to use the multigraph and I realized that the support for duplicated edges like that, 3 edges connecting 2 nodes, doesn't seem to be well supported. That's why I decided to use multi-digraph rather than multigraph to do this example. If in future I get it to work, then I can put a comment there in the videos. However, for you to be able to plot those 3 edges, you have to use a multigraph rather than a graph in NetworkX. So we can add nodes from the node set that we have already here as usual, and then we can add edges. Now for the first time we want to draw the labels of the edges. So from node 1 to 2 the label will be E1. So the way you describe it, if you add an edge, you can either just add an edge, or you can also add an edge with other parameters. For instance, the label parameter. Label is a variable here. You could have used anything and called it E1. Now the rad you see here is something to show whether this edge is going to be a straight line edge or a curved edge. If rad is 0, 0, it means that this edge is going to be a straight line edge. If rad is something else, like when we added 2 to 3, and that is edge 2, the first edge that goes from 2 to 3, there are 3 edges you should remember. So we can give it a radian, an angle, to indicate the curvature of the edge. It's not going to be a straight edge, it's going to be a curved edge. So we'll continue from 3 back to 2. E3, this one is going to be a straight edge, so the radians is 0. And then we went back from 2 to 3 again. This time around we use a negative radian so that the curvature is in the opposite direction of the first curvature. Both of them are in opposite directions. And we'll continue that way from 3 to 4, from 4 to 5, from 5 to 6, 6 back to 5 again, and 5 back to 6 again, then from 6 to 1. So let's record that for the post, we have been using the string layout ever since, that positions the nodes on the screen randomly, and that is the reason why every time we plot the graph using that string layout, we always get a different appearance of the graph. Now using this pose, you can actually decide where you want your nodes to be. If you want your nodes to be in exactly the same place, exactly the way the graph is, you specify the position directly by yourself. So this time around we are going to specify the position directly. So we are looking at something like a graph book that starts from 0, 0 at the middle. This is the y-axis and this is the x-axis. So from our graph is going to be like this. We have several nodes here like this. You determine the XY, suitable XY positions that you want the nodes to be, and every time you plot it, they are going to be exactly like that. So this is node 1. First of all, you take the node and then you describe whichever location you want the node to be. So what we have here is our graph sheet, and this is node 1. We can say node 1 is at x equal to 6 and y equal to 12, and then node 2 is at, this is node 2, is at x equal to 10 and y equal to 10. We are coming down on the y-axis and we are moving further on the x-axis. And you know definitely node 3 will be also at x equal to 10, and we can bring it down to at y equal to 4. That's node 3. And you know now that node 4 will be definitely at x equal to 6 and at y equal to 2. We'll bring it down to 2. That is node 4. So node 5 will be at x equal to 2 and y equal to 4. And node 6 will be at x equal to 2 and y equal to 10. So every time you plot the graph using this pose, it will remain the same as it is supposed to be. It doesn't change. So we can draw the network using this pose and G. And we can also draw the network labels. So the network labels are the ones that put your 1, 2, 3, 4, actually writes it to the graph. Now, for us to be able to plot the edges this time around, because we want to use the labels of the edges, use this for loop to do that. We are going to plot the edges one by one, and then we'll write the labels on the edges. So we say for edge in g.edges, data equal to true. Later when we run this program, you know the reason why we say data equal to true. So the edge data contains some information. First of all, it contains the two nodes that form the edge and some other information, all the other information that we created, that we defined when we were creating the edge. All of them will be additional information. So to get everything, both the nodes and every other information, you use data equal to true. Now we are only printing this just to show you, for the purpose of learning, what is actually returned, that it is the list of everything that you see here. So we can now say nx.draw NetworkX edges. You can Google the documentation on this draw NetworkX edges and you can see all the parameters you are supposed to enter. We don't need to use all of them. Only the ones that are important for us to be able to draw the graph is what we are using here. First of all, you put the graph, and then you put the pose that will show where it is plotted, and then you take the edge list. So the first two items that are returned from the edges is the first node and the second node that are connected. Then you specify the connection style. So we are going to use arc3, and then specify the radius. The radius is coming from the same parameter you have here. So we say edge 2 rad. So what happens is, whenever you return edges, the first two nodes are given as the first two items. In fact, it's going to be two nodes that an edge connects. They are given as the first two items. And then the third item contains whatever parameter you define. If you define 3 parameters, you will get 3 items. If you define 4, you get 4 items. So we defined only 2 here. And the keys are label and rad. So from edge 2, if you want to specify whichever one, you pick it and put it here. This time around, we are specifying that what we want from edge 2 is the radians. So every time it loops through here, it's going to pick the exact angle that is specific for that edge, specifically to plot. So we can now define the edge label. Edge label is going to be a dictionary. This is the key of the dictionary, and this is the value of the key. So we are using the label key here, E1, E2 to E10. We now say nx.drawNetworkX labels. G pose edge labels equal to edge lab. You will use this. It is required. You can Google the documentation on drawNetworkX edge labels. Label position 0.6. Now, if this is an edge containing two nodes, the label position specifies where along this line the label should be written on. So the line starts from 0 and it ends in 1. If you say 0.5, the label will be written exactly in the middle. If you say 0.6, the label will be written somewhere beyond the middle. If you say 0.1, the label will be written somewhere close to the source. Okay, so we say horizontal alignment left, vertical alignment center, rotate equal to true, either true or false. Whether the label should be rotated or not rotated, you can say true, you can say false, it doesn't matter, depending on which one appeals to you. And you can specify the font color that is going to be used to write the label on the edges. So you can now show your plot. So we are going to go to Visual Studio Code now and run the program and see exactly how it works. So here we are in Visual Studio Code, and this is the program that I just described before. So no need to describe it again. Here it's a short, simple program. We are just going to plot it and see how it runs. So I click run. This is the graph. So you can see that every time you plot this graph, it's going to look like this because we actually specified the exact positions of a graph on the screen. Now, somehow the edges are not well arranged on this side. I have not figured out how to do that yet. I couldn't find an example on the internet that actually did multi-graphs, multi-digraphs. So I will explore that further. However, for that reason, one of the edges that is supposed to be plotted here is not shown, and the edges are actually not located exactly when you have duplicate edges. So for now, at least this looks close to the graph that we have in the presentation as much as possible. So we continue with Eulerian and Hamiltonian graphs. We look at Eulerian graphs equivalent statements. In a graph G equal to VE, the following are equivalent. G is Eulerian. G is connected and each vertex has an even degree. G is connected and there exists a partition E such that the edges in each subset of the partition constitutes a cycle in G. G is connected and each edge in G is an edge in an odd number of cycles in G. It is left for you to look at the graph we just demonstrated, especially the second graph, which is actually an Eulerian graph, and try to prove whether all these statements that are written here are correct. Let's see how to obtain an Eulerian circuit by hand by using an algorithm called Fleury's algorithm. The steps are as follows. Number 1. Initially we set I equal to 0, that's the first, and then we start from a particular vertex in the set, in the graph, we call it V0, and we define a set which is going to be a trail that has V0 as the first item. Let Ti equal to V0, E1, V1, E2, V2 up to Ei, Vi be the trail between Ei and Vi at step I. Select an edge Ei plus 1 joining Vi and Vi plus 1 from Ei equal to E minus E1, E2 up to Ei. If Ei plus 1 is a bridge in the subgraph obtained by the action of Ei, then select it for inclusion in the updated trail Ti plus 1 equal to V0, E1, V1, E2, up to EI plus 1, VI plus 1, only if there is no other edge. If there is no such edge, stop. Now we are in step 3. Replace I by I plus 1 and go to step 2 and continue. Example 2. We are now going to obtain an Eulerian circuit from the graph we are seeing here. We'll do it by hand by using Fleury's algorithm. So, first step, iteration 1, we are going to choose a vertex V2 as V0. It doesn't necessarily have to mean that you must start from the first vertex. We start with vertex 2 and then we choose H24 and we set H24 as E1. So that's what we have here. Vertex 2 becomes V0 and H2 becomes E1, and we delete it. Delete 24 and set the previous vertex 4 as the new current vertex V1. So we already have V0 and E1 as a part of T, and then we'll continue from the previous graph. So that's what we have here now. The current vertex is V1. Select V16, which is this one, delete and set vertex 6 as a new current vertex V2. So we are now obtaining E2, and this is what we have. Gradually we'll be deleting the edges one by one until we don't have any edges left, and then we'll know that we have obtained an Eulerian circuit. We'll go to the next stage, continuing. We now select V2 and 5 as E3, and then we delete it and set vertex 5 as a new current vertex V3. Continue from there. Iteration 4. Select one of the edges between V3 and 3 as E4. Delete it and set vertex 3 as V4. So this is the one we selected. We delete it. Set vertex 3 as V4. So we have now obtained E4. E1, E2, E3, E4. Continue from there. Select one of the edges from V4. Don't select a bridge. For example, you can select V4, V1. See, this is a bridge. Make sure you don't select a bridge. You have two other options. So you can select V4, V1 as E5. Or you can select V4, V3 as E5. So let's select V4, V1. Delete it and update V1 as V5. So our former V1 has now become V5. We'll continue from there. So you can now select bridge V5, V3 as E6. Delete it. This is a bridge. V5, V3 as V6. And that's what we have on this side. We'll continue with that. Select bridge V6, V4. V6, V4. Delete it and update V4 as V7. That's what we have here. Continue from there. Select bridge V7, V0. V7, V0. Delete it and update V0 as V8. Continue from there. Iteration 9. Select bridge V8, V1. Delete it and update vertex 1 as V9. Select bridge V9, V2. Delete it and update V2 as V10. Select bridge V10, V8 as E11. Delete it and update V8 as V11. So after you have deleted all the edges from the original graph, you can now check the sequence of edges that you created, E1, E2, E3 up to 11, and you can check whether the circuit is an Eulerian circuit by the definition of an Eulerian circuit. So the sequence of edges which were obtained, E1, E2 up to E11, is an Eulerian circuit. Let's go through them. We went through E1 and then E2, and then E3, and then E4, and then E5, and then E6, and then E7, E8, E9, E10, E11. This is where we started from. We came back to where we started from. So that shows that the sequence we obtained here using Fleury's algorithm is actually an Eulerian circuit. Now let's consider Hamiltonian graphs. We begin with a Hamiltonian path, which is a path between two vertices which passes through every vertex of G. A Hamiltonian cycle is a closed Hamiltonian path. A Hamiltonian graph is a graph that has a Hamiltonian cycle. Every Hamiltonian graph has a Hamiltonian path, but not every graph that has a Hamiltonian path is a Hamiltonian graph. The converse is not true. Every cyclic graph is a Hamiltonian graph. Every complete graph with 3 or more vertices is also Hamiltonian. A complete bipartite graph K subscript Mn is Hamiltonian if and only if M is equal to N. That is, there is an equal partition. We look at Orez and Dirac's theorems. A sufficient condition for a graph to be Hamiltonian. Dirac's theorem. A simple graph with n vertices where n greater than 2 is Hamiltonian if the degree of every vertex is at least n over 2. Orez theorem. A simple graph with n vertices where n greater than 2 is Hamiltonian if the sum of the degrees of every pair of non-adjacent vertices is at least n. Tournaments. Remember, we described tournaments before, it's not the first time. A tournament is the digraph obtained by converting each edge of a complete graph Kn into an arc. That is, an orientation of a complete graph. Such a digraph can be used to record the results of games in a tournament, in which each team player plays against every other team player in a match, such that no match ends in a draw. If the match between two teams ends in a draw, they continue to play against each other until one of them becomes the winner. A typical vertex Vi represents a team, and the presence of an arc from Vi to another vertex indicates that in the match between Va and Vj, the winner is Vi. So, if we draw the direct graph and an edge is moving from Vi to Vj, it means that Vi is winning and Vj is losing. The out degree of a vertex Vi is the number of matches in which Vi is the winner, and its in degree is the number of matches Vi lost during the tournament. Now, let's look at Reday's and Camion's theorems concerning tournaments. Reday's theorem. Every tournament has a directed Hamiltonian path. Please try to be proving all these definitions we are creating by using simple graphs. Camion's theorem. A tournament is Hamiltonian if and only if it is strongly connected. Now let's determine the best and worst teams of the tournaments shown below. So if we look at the UEFA Champions League, this is Barcelona Football Club, this is Paris Saint-Germain, this is Inter Milan, and this is Manchester United. You can use the graph to determine which of the teams are winning and which of the teams are losing. So in the description we did previously, if an edge is coming from a particular vertex, in this case FC Barcelona is a vertex here, every other team is also, there are also vertices here. If the arrow is coming from a vertex and going out, it means that the team is winning. If an arc is coming back, then the team is losing. So we can see that FCB is winning 3 matches here, is winning against the other 3 teams. PSG is winning 2 matches and losing 1. Inter is losing 2 matches and winning 1. and Man U doesn't seem to be doing fine in this tournament. Now, based on the explanation I've given here, can you be able to determine which teams are winning or losing in this NFL league? Try that and let's see. Before we go, we'll look at how to read and write network files using an edge list file. So, what we have been doing since is we just write everything, the edges and the vertices, directly in the code. Now, if the edges and the vertices are very large, it will be tantamount to manual labor for you to be typing all the edges and vertices by hand inside the program code itself. In such cases, you can put the network data in a file so that you can just read it from the file that is stored somewhere in memory separate from the program itself. So what we are trying to do is to learn how to read network data from files. Several file formats we can use. They include an edge list file, which we see in this class, adjacency list file, GEXF format files, and JSON files. We will not be able to go through all of them, so we'll just consider using only edge list. The rest of them are similar, which you can explore in your time. So here's an example edge list file. This is the first map we saw when we were trying to look at the path map of a campus environment. So you just define the vertices by using their real names. In this edge list file, the first thing that should show is the name of the file, which you are going to use to read it. And then you may put a description of the file. Doesn't matter whether you put it or not, but it is advised to put a description. Now what you see here is source, target. These are two parameters that defines whatever is going to be read from the file. So here we have a set of vertices. Just vertices alone describe the file, or we can say a combination of two vertices makes an edge. So what we actually have here is a list of edges. From gate to the 1000 lecture theater is an edge. Just tells you that this edge is connecting the gate to the 1000 lecture theater. And then from there we'll go to needs assessment, and from needs assessment to admin block, just like that. And we'll learn how to read this file in our NetworkX and plot the graph. So how do you create this file? You create a plain text file and save it as a .edgelist. You can use Notepad. In fact, use a program that will not put any formatting. We just want an edgelist file. Something like Notepad or TextPad is okay to use. So you keep the file in a directory, and then you can write the program to read the file and plot the graphs, rather than describing nodes and vertices inside the program. So we'll call this edgelist.py. We will import OS because we are going to use it to know the directory where it is stored. And we perform all the other necessary imports as usual. So we are going to get the current directory where this Python code is executing. In case you don't understand how to do this, please watch my previous videos on Python programming, and then this one will become clearer. So as usual, we assign a file name. I did not store this edgelist file directly in the directory where the code is stored. Rather, I created a data directory inside the directory of where the program code is running from, and inside that directory, that's where I kept all the edgelist files. That's why we have what we have here. To create a graph, we just say g is equal to nx.read edgelist. Put the file name here, and you can draw the network. So we use our spring layout here. If you want the graph to look exactly the way you know the campus map, then try to estimate Cartesian coordinates for each of the vertices there, and then you don't need to use this spring layout. You can follow the first example program that I gave to plot it to look like that. So we plot that figure 1, and then we draw the network. So we plot the G. The first plot that we did when we said read edge list is for an undirected graph. It creates an undirected graph. If you want to create a digraph, you say nx.readEdgeList, and then after the file name you say create using nx.digraph. So you see the difference on how to create an ordinary graph and how to create a digraph. We actually added another parameter in the read edge list when we called the method. So we plot it. We now have a digraph. You can now draw NetworkX for the digraph, and you may try to get the current axis if you want to use it. This is not really important, and then the important thing is you show the plot. So from here we are going to go to Python and see how the plot really looks like when we do it. So here we are in Visual Studio Code looking at the program which I just described. I will run it now and we see the two graphs come out. So the first graph to be plotted is the ordinary graph, and the second graph to be plotted is the digraph. This is the ordinary graph, and this is the digraph. Let's look at a weighted undirected graph. We are still going to use an edgelist file to plot a weighted graph, so we are looking at a different edgelist file now, the same map. This time around our parameters are not just the source and the target like the previous one. So we have a source, we have a target, and we're also going to include a weight in the file. This is the edge from gate, or the edge between gate and 1000 lecture theater. The width is going to be 12. For the second one, the width is also going to be 12. For the third one, the width will be 10. So the road size is getting smaller. It depends on what you want to do. You can make it big, 100, whatever, as much as you can. So let's see the Python program for that. We'll call this program plot edge list weighted.py. As usual, we'll perform our imports, and then we'll get our current directory to get the file name. Then we assign the file name as usual. But when you are reading the file this time, instead of just saying read edge list like the previous example, we actually say read weighted edge list, and then we can set our Spring layout again if you so wish, and then we'll perform some other operations. We extract the weight equal to d weight for std in edges data equal to true. See, I explained this before in the first code where we were trying to plot labels of the graph, the first graph. So remember, in the file 3 parameters were defined. Inside e.edges, pick the weight out, and we are going to put it in a list called weights. We are just printing it to know which weights are actually shown for the purpose of learning, not for the purpose of plotting the graph. We'll continue. So we'll create our figure, and then we'll draw the NetworkX. We'll print the weights again to see for the purpose of learning, and then we are now going to draw all the edges one by one using the weight data. So we say for edge in edges data equal to weight, it is going to pick the edge data, that is the two nodes, together with the weight along. So let us print edge 2 and see what actually comes out. Remember, there are 3 data. So there is edge 0, which is the first node. There is edge 1, which is the second node, and there is edge 2, which will be the weight in this case. So we want to use that edge 2. We now say nx.draw NetworkX edges pose edge list. The edge list is going to be all the edge parameters that were returned from here. It's not only weight that is returned here like I described before. There are 3 things. So we say edge color equal to edge, but this color doesn't seem to work. I have not yet figured out why it's not working exactly. It plots everything in one color, but what is important for us here is we want to plot according to the width. So we say width equal to h2. This one works, and that's exactly what we wanted to do. You can now show the plot. So we will go to Visual Studio Code and try to run this program and see exactly how it works. So here we are in Visual Studio Code, and this is the program that I just described. Very brief. Run the program. So you see the plot that we got from this. All the weights are actually indicated. So we have a weight from the gate to 1000, lecture theater, to needs assessment, to the workshop, which are actually smaller roads. And this one is just a footpath for a few people. A vehicle cannot drive through this route, and you can see how tiny it is in the graph. This one can accommodate several vehicles, maybe 2 or 3 vehicles running at the same time on this lane. The lanes get smaller. Okay, now let's look at the outputs of weights that actually came out from here. We are plotting the weights several times. So we have 22 here, 12 here, 7, 10, 7, 10, 5. I actually changed the file, which is different from what I described in the example. In fact, this will make us to understand it better. So if you look at the directory of the files, this is the code directory of where I'm running the program from. Here are the Python files. I didn't keep the weight files directly inside here. Rather, like I said before, I kept them in a data directory. So this edge list file is the one we just ran now. I'm going to right click it and open it with a program that can open it. You can't open it with Microsoft Word or any of the elaborate programs. Rather, you can open it with a simple text editor like TextPad or Notepad. So if we try TextPad, this is what we get. Okay, although I used 12 for the first edge in the presentation, it is actually 22 here because I changed it to make it bigger, so you understand the way it is. If you want to create an edge list file just like the way it is in the presentation, this is how you do it. But when you save it, you say save as. Make sure that you don't select a particular file format. No, don't select text files or whatever file format. You say all files, so it doesn't have a format. And then you give it a file name and you will say dot edge list and then save it. If you use Notepad or TextPad, it is going to save. Okay, so we just printed the edge file several times for the purpose of learning. As you can see from the graph, the color did not show. It showed only one color. Don't worry about that. Later we'll learn how to plot color graphs so that we specify the colors directly. For those who are familiar with a particular environment, what I want you to do here is actually see whether you can create an edge list map of your environment, particular area where you are staying. Pick up some buildings, pick up some roads, and see what you can do with it. So before we end the class today, let's look at the homework stroke lab 3. This is the third one we are having. The edge list graph shown previously is not complete because some major buildings, roads, and footpaths covering the area shown in the original graph were not listed. Complete the edge list according to your knowledge of the environment and use it to plot a graph, an ordinary graph, plot a digraph, the examples we just saw. Also perform the following. Rearrange the map according to the approximate locations of the buildings with the gate at the top as a reference point. Plot a weighted graph in different colors. Make sure the weights assigned roughly reflect the size of the roads stroke paths, and make sure all edges are labeled as E1, E2, so on and so forth. So before you do this homework, I am going to show an example of how to plot the edges so that they will not only show the weights, but they will also show different colors representing the edges. So here we are in Visual Studio Code, and we are looking at a program that demonstrates how to plot the weighted graph in different colors. As usual, we'll perform all our imports, and then we create our directory and select the file name. So this file name is, we call it DOU part 2 colored edge list, and then we read the edge list differently. So see the way we read it: file name data equal to weight float, and then we also say color string. We are going to read both the weight and the color, and the different data types are shown here. We select our spring layout again. Remember, in the homework that I gave to you, you are not going to use spring layout. You are going to actually try to look for specific locations in the Cartesian coordinate that looks like what you are trying to describe, so that every time you plot the graph, it will remain in that position. So the next thing we are going to do is extract the colors and keep it in a list, because we will use it later. We will just print the colors to show the colors that were defined. Then we'll draw the network. So now we are going to draw the edges and show the weight of the edges. Everything you see here, except for a few things, is actually from the previous example we have seen before. We are only printing edge 2 here to know the size of the edges for the purpose of learning. So we draw the network. We set a variable k is equal to 0, which we are going to use to iterate through the colors so we can print the colors. Like I told you before in the previous graph, the color was not showing, it just printed everything in black. So if you actually define colors in the edge list file, which I will show you, you can call the colors. See, we have already put the colors in a list. So why don't we just call the colors directly from the list? So you can see, as a part of the draw network edges, you specify the edge colors and use colors k. So k is iterating colors 0, 1, 2 up to the full size. And as usual, you do the edge. Then you show the graph, which is important. Before I will run this program, I am going to open the file we are using here. The file name was DOU part 2 color.edgelist. So if we come here and open DOU part 2 color.edgelist, open with textpad. So in the definition of this file, we'll give it the file name as usual. You must do that, and a comment that says what the file is doing, and the parameters: source, target, which must be there, weight, color. So you see where the color is coming from. From the gate to 1000 LT, the weight is 22 and the color is red. The other one, the color is orange, blue, green, red, orange, blue, green, red. Maybe you can change the colors to cyan, gray, so on and so forth, so that you can know whether your program is running very well. Now we are going to run the program and see how it works. So this is how our graph looks like. We actually plotted everything in color. As you can see, both the weights and the colors are shown. Now in the homework I gave to you, the major part you are supposed to perform is, if you know the environment very well, try to arrange everything in Cartesian coordinate. The gate should be on top and then you are coming down. Now in your own area where you live, like I have said before, try to create something that is similar to where you live and see whether you can get it, and arrange it in a Cartesian coordinate the way you know the environment. So our bibliography remains the same: the book of Balakrishnan, the book of Edward Platt, and the book of Filippo Mengsa. Other materials, be sure to check out the YouTube video tutorials and other online tutorials. So please like, share, comment, and subscribe for more videos. Thank you, and see you in the next class.